All right. Yeah, pizza would be awesome. Costco pizza's not bad. Dilations. Mm-hmm. All right, so we're going to do exactly what we did for the last three transformations. We'll talk about what they are, how we use math to describe these, and then we'll do a couple of examples. Dilations, I think, are the easiest. To me, they're the easiest. Translations are pretty easy, but dilations, I think, are a little easier. All right, so we want to know what it is. A dilation is a transformation with a center of dilation.
Is it sharp yet?
No.
Oh yeah, that's
We call their center of dilation C. And a scale factor. N. And for what we're going to do, we're going to say our scale factor is going to be positive. So I'm going to say n is greater than 0. Where these things happen. 1, the center is its own image. So just like a rotation, the center, when we do a dilation, it doesn't change. The center stays where it is. For any other point, P prime, the image is on the ray CP. And we'll draw a picture in just a second to show what this is telling us visually. It might sound a little complicated. It's really not. And the length of CP prime, from C to P prime, is the scale factor times the length of CP. So what we're saying here is lengths are multiplied by n. So thinking back to what we did right at the beginning of the semester, what was another subject, another topic that we studied where we multiplied lengths by a scale factor? You remember? If we had a figure, one figure is 3 times as big as the other. One figure is a half as big as the other. When we talked about similarity, right? We made ratios of the sides, multiplied the sides of one by 2 to get the sides of the other, something like that. So dilations have something to do with similarity. All right, let's draw a picture of what this is telling us. So we have a center of dilation. Here is my center, C. And we know that doesn't change with the dilation. And we'll dilate a triangle. So we'll do triangle A, B, C. So there's my triangle. Well, it tells us that the image is on this ray from C to P. So we do a ray from the center through each point. So there's one ray, there's another ray, and there's a third ray. So we make those rays from the center through each vertex. And then our new point, we find our new point by multiplying the distance from C to A. Why don't I call this, instead of 2 C's, A, P, B. So I don't have 2 point C's. the distance from here to here, we multiply by the scale factor. So I'm going to try to do it approximately 2 times as big. So whatever this distance is, I'm going to go make the ray from the center to the new point twice as long. So I'd have A prime there. The distance from C to P, I want to go 2 times as far, so that's going to take me about out to here. I'm doing this kind of by eye. The way you do it accurately is you would measure those distances. And from here to here is about, if I double it, it's going to be about here. And my new triangle, I'll do that in green. Whoops, make that solid. There. And that would be my new triangle.
So you use double where it's from.
So yeah, here I tried to make this about the same. This, if it were a scale factor of 3, I'd make it 3 times as long.
Oh.
If it was a scale factor of 4, I'd make it 4 times as long. So the distance from here to here is about twice what it is from here to here. So if this were 2 inches, that's about 4 inches.
Wait, so
If this is 5 inches, this would be about 10 inches.
Wait, so does it change every album?
Yes.
Alright.
And if I made the scale factor here too, then the green triangle would be twice as big as the black triangle. And our scale factor N would equal, we can make a ratio, C prime A prime over C A. The distance from C to A prime divided by the distance from C to A. And that's going to be the same as A prime B prime, the length of this, divided by AB. Same as, so we're making the ratios of corresponding parts. We could also say that's we could also say P prime B prime, this side, divided by PB. So any of the sides, any of these lengths would be the same ratio. And that would be, that ratio would be the scale factor. So dilations are not rigid transformations. They keep the angles the same, but the lengths are not. So for dilations, angles are the same. Lengths are not. So it is not a rigid transformation. The green triangle is not congruent to the black triangle, but they are similar. The green triangle is similar to the black triangle. And the scale factor here, I tried to make it about 2. All right, so questions there about what a dilation is. Now, luckily, for most of what we do, we won't have to do this stuff with the rays. All right, we call a dilation an enlargement. If n is greater than 1. So if our scale factor is bigger than 1, our image is bigger than our pre-image. And we call it a reduction if 0 is less than n less than 1. So that means a fraction between 0 and 1. So we get a reduction if our scale factor is 1/2, 1/3, 3/4. We get something that's smaller. So pretty easy idea, enlargement or reduction. In our book, this is what makes dilations really easy. in our book, all dilations, unless they tell you otherwise, have a center at the origin. And what makes this nice is, in this case, all we have to do to find our new coordinates, we multiply the coordinates by the scale factor. That's all we have to do to find our new coordinates. And we write capital D for dilation. This would be the scale factor of a point. All we have to do is multiply each of these by 3. So a dilation by a scale factor of 3 of the 0.35 is the 0.915. And that's all we have to do to get a dilation. So on your project, if you decide to make your dilation with a scale factor of 3, you just multiply all the coordinates of your original figure by 3, and you have your dilation. You plot those, and you're going to have a figure that's 3 times as big as your original. So this is what makes dilations, the way that we're going to do them, pretty easy. All right, questions? Okay, I just want to go through a couple of examples, and then we'll be done with chapter 9. So for this one, we want to know if this is a reduction or enlargement. And we want to find the scale factor. And I'm going to say we're doing some dilation of some scale factor of triangle ABC. And we know that equals triangle A prime, B prime, C prime. And I'm going to draw a picture here. Oops. So here are my points. B is at 4, 0. A, sorry, this should be 0, 4. I did that backwards. A is at negative 4, 0. And C is at 2, negative 4. So there's my original. There's my pre-image. And here is my image. There's B prime at 0, 2. There's A prime. So we know already, right? What is it, an enlargement or a reduction? It's got to be a reduction. And C prime is negative 1, negative 2. So there's my new triangle. Yeah. Negative 2, 0. It got kind of crowded there. So we know that's a reduction. So it got smaller, so it has to be a reduction. What's the scale factor? And remember, for it to get smaller, our scale factor is a fraction between 0 and 1. So it'd have to be what? 1/2. And we can tell that by just pick one coordinate. What do we have to do to 4 to get to 2? We have to divide by 2. So n equals 1/2. So that little triangle is half as big as the big triangle. And if we made a ratio of the sides, each of the sides of the small triangle would be half as big as the sides of the big triangle. All right, questions there? All right, let's do a problem similar to our opener. So let's say triangle XYZ has vertices. This is going to be how you do these dilations on your project. X is 1, -2. Y is 2, 3. And Z is -3, -2. And we want the coordinates of dilation scale factor 4 triangle XYZ.
But do you only multiply the x or y coordinate, or do
You multiply everything.
Alright.
Yeah, just you multiply everything. So all we have to do is multiply by 4. So x prime is going to be 4, -8. Y prime would be 8, 12. And Z prime would be -12, -8. Plot that new triangle, and you'd have a triangle 4 times as big as triangle XYZ.
Plus.
All right, questions there? So the multiply thing, I think that's what makes dilations really easy. You just multiply everything by one number. You don't have to worry about the x's and y's. You don't have to worry about a direction. Just multiply by a number. All right, one last type of question. What if we had two figures and we wanted to find the center of dilation? So I'm going to say this is A and this is B, and we know that A prime, B prime is a dilation. And I should say segment A prime, B prime is this dilation of segment AB. And we want to find the center. Any ideas? You might be. This doesn't really have to do with coordinates. It's just with our picture. Let me go back a couple pages. And let's look at this picture again. Look at that. Think about that, how that might help us with this problem. Does that give us any ideas? Well, that we want to find point C, but we know, yeah, Isabel?
Could we try to subtract the line of A prime and B prime from line AB?
Kind of, I think, kind of, sort of, that's what we do. But remember that the center A and A prime are all on the same ray, right? So let's draw a ray that goes through A and A prime. The center has to be somewhere on that ray. And we know that B and B prime and C, the center, are on the same ray. So let's draw that ray. It's really that easy. Where those two meet is the center. The center has to be on the rays between those two. Just find where they meet. So just draw them in, figure out where they meet. All right, questions? Any of you ever take photography class here? Yeah. So when you use the enlarger for your pictures, this picture is exactly what the enlarger does. This is your light bulb. This is your negative. It shines through the negative onto a plate that's further away. So in another photographic sheet that's further away, and that's how you get an enlargement. Those rays, just like this. So that's an enlarger. It works exactly like this. All right, homework. There's that.